Hello, everyone, and welcome to the show. I'm Hari.
And I'm Kimi. Today we're diving into the absolute ultimate cosmic mystery, black holes. They aren't just science fiction tropes. They are real, mind-bending regions of space-time where gravity is so strong that not even light can escape.
Exactly, Kimmy. And did you know the concept actually dates back to the late 18th century? Long before Einstein, an English clergyman named John Michell and French scientist Pierre-Simon Laplace independently imagined dark stars so massive that their surface escape velocity would exceed the speed of light.
Right. Michell even suggested we could find them by watching how they gravitationally tugged on nearby visible stars. Talk about being ahead of his time. But the actual math started in 1915 with Albert Einstein's theory of general relativity, though Einstein himself was famously skeptical. He actually published a paper in 1939 trying to prove black holes couldn't exist physically.
It is quite ironic, isn't it? Meanwhile, Carl Schwarzschild solved Einstein's field equations for a non-spinning star while serving in World War I, finding a singular radius that was once thought to represent infinite curvature, though physicists now clarify it is merely a coordinate singularity, where the actual space-time curvature remains finite. Later, J. Robert Oppenheimer and his student, Hartland Snyder, showed in 1939 that an imploding star really would collapse past this Schwarzschild radius, appearing frozen in time to outside observers due to intense gravitational time dilation.
And then we get the famous name. While John Wheeler popularized the phrase black hole in the 1960s, the physicist Robert Dicke actually compared them in the early 1960s to the infamous Black Hole of Calcutta, a notorious prison where people entered but never left alive. A bit grim, but certainly descriptive.
Very vivid. Once the golden age of black hole research kicked off in the mid-1960s, physicists realized these objects are incredibly simple in terms of their stable properties. Under the no-hair theorem, a stationary black hole only has three independent parameters: mass, electric charge, and angular momentum. You could make a black hole out of library books or raw plasma, and once it collapses, they are completely indistinguishable if those three numbers match.
It is wild to think about, and they spin incredibly fast. Take GRS 1915 plus 105, a stellar mass black hole estimated to rotate over 1,000 times per second. Even our galaxy's central supermassive black hole, Sagittarius A star, rotates at about 90% of its maximum physical limit. That spinning drags spacetime around it like a vortex, creating a region called the ergosphere.
Ah, the ergosphere. That's where frame dragging is so powerful that you literally cannot stand still. But interestingly, through the Penrose process, an object can fly into the ergosphere and escape with more energy than it started with, stealing a bit of the black hole's rotational energy.
Cosmic energy piracy. I love it. Now, what about the structure? We always hear about the event horizon, but there is also the photon sphere. This is a boundary where gravity is so strong that photons are forced to travel in orbits. If you stood there with a flashlight, the light would loop around and you could technically see the back of your own head.
That would be a bizarre selfie, Kimi. And when telescopes like the Event Horizon Telescope imaged the supermassive black hole in the galaxy Messier 87 and later Sagittarius A, they didn't see the horizon itself. They captured the black hole's shadow cast against the brilliant backdrop of the hot, glowing accretion disk.
Which brings up the active galactic nuclei, or quasars. These are powered by supermassive black holes swallowing matter. Friction heats the infalling gas to millions of degrees, making them some of the brightest objects in the entire universe. Yet inside, there is a singularity where the laws of physics break down.
Unless quantum mechanics saves us. Theories like loop quantum gravity or the string theory fuzzball model suggest there might not be a true singularity with infinite density. But without a unified theory of quantum gravity, we're stuck with the famous black hole information paradox, originally highlighted by Stephen Hawking.
Right, because if black holes evaporate via Hawking radiation, and that radiation is purely thermal, all the detailed quantum information that fell inside is seemingly lost forever when the black hole vanishes. It violates quantum mechanics. Scientists are still fiercely debating how this gets resolved.
They really are. And speaking of evaporation, did you know that stellar mass black holes are actually growing right now, even if they aren't eating stars? They absorb more heat from the cosmic microwave background than they can ever radiate away. A black hole would need to be smaller than our moon just to start shrinking in the current universe.
That is a fantastic little-known fact, Harry. We also have some incredibly weird theoretical alternatives to black holes, like gravistars, which have a dark energy interior, or nestars, which are gravistars inside other gravistars. It's like cosmic Russian nesting dolls.
Exactly. Whether it's the first direct detection of gravitational waves from merging black holes by LIGO in 2015, or the Nobel Prize in 2020 awarded to Roger Penrose, Andrea Ghez, and Reinhard Genzel, black holes continue to dominate modern astrophysics. Absolutely. It's a fascinating frontier of human knowledge. Thanks for joining us today, everyone. We hope you enjoyed this deep dive into the abyss.
Take care, keep looking up at the stars, and see you next time. This episode is based on the Wikipedia article Black Hole, which is available under the Creative Commons Attribution Share Alike license. This podcast was crafted using artificial intelligence.